We spent some time talking about line integrals and exact differentials. In this video, we want to continue that discussion, only kind of broaden the implications of what it means to be dealing with an exact differential. And to get us started, let's pretend that we have an isolated positive charge here, and then out here we have a test charge, also a positive charge, and this test charge is going to be moved from point A to point B along this path. Now, the force that the test charge experiences from the stationary positive charge that's this. Here is the test charge. There's a stationary positive charge, r squared 4 pi epsilon naught. I think it's called the permittivity of free space, where r, of course, is the position vector corresponding to different points along the pathway. Here we're at point A, so this is RA. We end up at point B, so this would be RB, and then here we are at some point along the pathway right here. We're calling this position vector then just R1. So the force that the test charge experiences is along the direction of that position vector, or that radial vector R1. And imagine that right here at that point we draw a line that's tangent to the curve at that point. And so right at that point, also imagine that we have a differential line segment, dl prime, that is tangential to the curve at that point right there. And this is difficult to sketch in, but imagine here we have in the position vector R1, and then almost immediately next to it, almost superimposed on top of it, we would have another position vector going out that would be at the end of that tangential line segment, or that differential line segment, dl prime. So here we have this drawn, expanded. Here is the differential line segment, dl, obviously greatly expanded. Here is the position vector R1, and then next to it, almost superimposed on top of it, would be the position vector at the end of that differential line segment. And that's what we have shown right here. The position vector going out to the end of the differential line segment, dl. Obviously, this is greatly expanded. Now, the vector that goes almost right next to R1, we're calling it R1 plus, and because it's so close to R1, again, it just goes to the very end of the differential line segment, dl. R1 and R1 plus, for all essential purposes, are parallel. Here they don't look parallel because we've amplified the differential line segment, dl, because we're trying to sketch some other things in. So if the particle, say, is sitting right here, the force is in this direction. If we want to calculate how much work is done, then we need to know the tangential component of the force times dl. Or that would be then F dot dl. F dot dl will be the tangential component of the force that would be parallel then to dl. And of course, F dot dl, that will be dw. And this would be the magnitude of F times this is the line segment here in vector form. Its magnitude, of course, is just dl times the cosine of theta. And the magnitude of the force, of course, that's just this. Here we would say, at the particular point where we're at, we would say r1 squared, but in general it's just over r squared. But let's look at our diagram more closely. Here's what we're trying to explain. Here is dl, and we can resolve it into a radial component, here dr, where dr is just right parallel with r1 plus. Remember, r1 plus is just the position vector that starts here and goes to the end of that differential line segment dl. So this we could break down into a dr component and a perpendicular component. Now, again, r1 and r1 plus, because r1 plus is so close to r1, it's almost right next to it, these are really parallel to each other. So let's look at it like this. Here is dl, and here is the dr component of it. That's this part, that's here. This is the vector r1 plus. This is the position vector r1. They're really parallel to one another. So here, this would be then the direction of the force. This is dl. We're taking f dot dl, so that will give the tangential component of the force along the segment dl, and that's what we want. That's what the work is, the tangential component of this. But f dot dl, what is that? Well, it's this times dl times the cosine of the angle between them. Let's look at it like this. Here we have f, but remember that is this expression. So we're taking the dot product of this with dl. Really what we're taking the dot product of is just this unit vector with dl. And the unit vector, that unit vector would be, it'd be here. That would be that unit vector r, or getting down to our current diagram of interest, it'd be right here, the unit vector r. So when we take the dot product, we're taking the dot product of this with dl. And what is that? It's the magnitude of this, which is just 1, it's a unit vector, times the magnitude of that dl vector arc, that's just dl times the cosine of theta. So when we're taking the dot product, f dot dl, the dot product of f dot dl, we can show it like this, the magnitude of f times that unit vector dot dl. And that will equal just the magnitude of this. The magnitude of this unit vector, of course, is just 1. That's just dl times the cosine of theta. But here's what we want to show is that dl times the cosine of theta is the same thing as dr. Remember, we had a differential line segment here, dl. Here it is greatly expanded and then broken up into a dr, that's a radial component, and a perpendicular. Then we realize that these two vectors here are really parallel to each other because this one, r1 plus, lies almost right next to r1 because it's going to the end of just an infinitesimal line segment, that differential dl. So we're trying to demonstrate that here. Here's the position vector r1, r1 plus. They're parallel to each other. So if this angle here is theta, then what that means is that this angle here is theta. And that's what we have demonstrated right here. And the reason why is these two are parallel to each other. So this and this are parallel. We drew this line here perpendicular to this one. That's right here when we were decomposing dl into its radial component. So it's going to be, this is going to be perpendicular to both r1 and r1 plus. So if this is angle theta, this is 90 minus theta, therefore this has to be theta. Well, we have the expression now dl times the cosine of theta. That's just dr. Here's dl, here's dr, there's theta. This times the cosine of theta is just dr. And that's what we have right here. So what comes out of all of this is that f dot dl, first it's that the differential amount of work done dw, that is f dot dl, and that equals the magnitude of f times dr. And the magnitude of f, that is 1 over 4 pi epsilon times q prime in general divided by r squared. We want to know the total work, so we want to integrate this. So we want to integrate dw starting at r equal a and going out to r equal b. So here we have r equal a out to r equal b. But this equals the integral of f, the magnitude of the force, times dr. The magnitude of the force is this. Q prime, and this, those are all constants, so we'll leave those to the outside of the integral. So we have q prime over 4 pi epsilon. Then we have the integral of dr divided by r squared. And r goes from a to b. Or we can take this, write it upstairs with an r to the minus 2. Let's do it like that. So r to the minus 2 dr. And of course this is a real simple integral. This is just going to be minus 1. This will equal q prime over 4 pi epsilon times minus 1 over r. R goes from a to b, or that will equal our constant here, q prime over 4 pi epsilon naught. We have a minus sign here, so that will be 1 over RA minus 1 over RB. And that's the total amount of work. Now remember, Q, that was our charge here, our stationary charge. Q prime was our positive test charge that we're moving along that path. But notice that the amount of work that's done depends only upon, this is RA, that was its starting position, RB, that was its position here at the end. So it depends only upon the amount of work that is performed going from here to here, only depends on this and this. The path that it takes is irrelevant. So for example, when we have the problem set up, here was our stationary plus charge, and then we had a test charge, and we were moving around like this. This is point A, this was point B. Well, the amount of work we perform depends only upon the position vector RA and the position vector RB. So we could have taken that path, and the amount of work performed would have been the same. It only depends upon RA and RB. It only depends upon where we start and where we end. The path that we take in between is totally irrelevant. Or, if we go back here, what happens if we end up where we started, so that RB equals RA? Then, of course, the work equals 0. So, we could start here. Here's our stationary charge. We could have a test charge, move it like this. This is A, this is B, and then move it back to point A along a totally different path. And the amount of work that we perform will still be 0. Now, remember in our last two videos when we were discussing exact line integrals, well, first remember the general way for writing a line integral, as you saw in our introductory video concerning line integrals, it could be some vector v dot dl, or we could have it the line integral v dot dr, where r is the position vector. And again, we went all over this in our introductory video on concerning line integrals. But the other way to write it is this is the other general expression for a line integral. And again, back in our introductory video, we derived this from this. But what we established in the past two videos when we were discussing exact differentials in line integrals is that if this is an exact differential, meaning that p dx plus q dy, this is the differential of some function f. Again, we discussed this in a lot of detail in the previous two videos. When this is true, the closed line integral is always 0. And as you just saw here, the work that we do, if we had calculated the work about going from, not from A to B, but going from A to A, where you have 1 over RA minus 1 over RA, the work is 0, or we have it like this. Does that mean then that the work that was performed in this electrostatic field when we moved the test charge from point A to point B, we calculated how much work that's done, but this is behaving exactly like an exact differential. That is, the expression that we get is independent of the path, and if we go all the way back to the beginning, the work is 0, just like it is when you have an exact differential. Or when we say we have an exact differential, as you saw in our previous two videos, what that means is this expression is the differential of some function. So does that mean then that work is the differential of some function? And the answer to that is yes. It's called the potential. And that's where the potential arises from. And whether you're in an electrostatic field or a gravitational field, it doesn't matter because they both have, the force involved has the same type of general expression. For the electrostatic force, we just have some constant here times the two charges divided by the square of the distance. Or if it's a gravitational force, again, it's times a constant in general form, mass 1, mass 2, divided by r squared. So gravitational force and electrostatic force, they both behave the same way. That is, the amount of work that you perform doesn't depend upon the path, it only depends upon the two endpoints, the beginning point and the final endpoint. What that means then is that in each case, the work that we do in an electrostatic field or in a gravitational field, that work is the differential of some function, and that function is what we call the potential. And again, we'll discuss this in more detail in future videos. We just wanted to introduce that concept here. And also, this is what a conservative force is about. That is that the amount of work that the force produces depends only upon the endpoints. It's totally independent of the path that is taken.